Video podcast for Chapter 4 of Field Methods in Hydrology. Now I know this is a field methods class, and our goal is to get out in the field and give you experience using a variety of different technologies that you need to make the important measurements that help us understand how water moves and is stored in the environment. But it's very important to understand that when we go out in the field, we don't just rush out and make measurements. Data is important, but data is not the most important thing. The most important thing for fieldwork is to have a very strong foundation for what the goals are that you want to achieve and the conceptualization of how you're going to use that data to solve whatever the problems are that you're facing. And that's why it's very important to understand what the types of field hydrology studies are before you start going out in the field. I already talked about the importance of historical analysis in Chapter 3 because that tells you the context of a site, the different styles of hydrological function that might be taking place. That's a great start, but once you have that conceptualization in mind, then you have to say, okay, well, what is it that I want to achieve in conducting field work, and how am I going to use that information? When we go out in the field, we're often not doing strict experiments in the sense that we think of from, laboratory biology or chemistry, although that is possible. Usually we're doing what I would just call field research, just defined here as the act of going to a location and observing what is happening there to aid the development of a conceptual understanding of some phenomena. So usually the data we collect helps us figure out, affirm, deny, just understand what is happening with some natural phenomenon with water. Sometimes we might be trying to collect data to make specific predictions, but usually we're not using the field data that way. There also can be more strict field experiments, and I'll use the definition here from a geomorphic context by Olive Slaymaker from 1982, who wrote that a field experiment is a set of measurements conducted under controlled field conditions to develop and formalize some general principle about the evolution of landforms. So for us, we're not so interested in landforms per se, as much as water flux, but still, both these definitions I've provided here for field research and field experiment share some commonalities in that they emphasize the importance of having a conceptual understanding before you go out and then using field data to test that. So when we think about science, we often think about some kind of controlled conditions. But how controlled is controlled? How can we do that? And what really makes something an experiment? Well, I think there are four main attributes of field research. So I'll list these and then I'll describe them a little bit more. The first is, and I've already been saying this, that measurements have to be made in the context of an explicit conceptual model of the processes of interest. You have to have an idea before you even start. If you don't, make something up. It doesn't matter. But you got to have something. Now, why is that? Well, first, it gives you a real focus to what you're trying to do. Second, it puts some what we call skin in the game. You're challenging yourself, and if the data proves you wrong, you don't like that. Humans don't like that. So, putting yourself out there helps to focus. It's also important because if the data isn't going to answer the questions you're setting out to address, then why bother? So you have to have a conceptual model because you or your clients or funding sponsors are going to be trying to solve problems, and they want to believe that you know what you're doing, and a conceptual model helps with that. Next, you have to have specific testable hypotheses that should be formalized about the process or thing you're trying to study. Now, oftentimes we start with goals and objectives. That's fine. Those can turn into questions, and of course any question can be inverted into a statement that is essentially a hypothesis. A hypothesis is just nothing more than a statement about what you think is true, and then you can test that. The measurement procedures that you do must bear on the hypotheses. Now that sounds obvious, almost stupid, but you wouldn't believe how many times I review manuscripts for scientific journals in which the data that they talk about have nothing to do with the questions, or they simply didn't pose questions in the first place, or they weren't good questions, or they found some wrinkle that they want to talk about that aren't part of the experimental design. That's not good implementation of science. Finally, analysis procedures have to use the data to test the hypotheses and thus address the conceptual framework. So this closes the loop. In other words, a lot of times I'll read proposals or ideas that people have in which they have really good questions and they know exactly what kind of field methods they're going to use to address that. But they just haven't thought through the tests that they're going to apply. What range of values for each variable in a test leads to a certain interpretation? For example, does a big number mean my hypothesis is correct? How big does the number have to be? Does it have to be different from other numbers? So knowing those sorts of thresholds for the test variables is important. Okay, so let's put some meat on those bones. First, let me show you a relatively simple example of a conceptual model that can be used to aid fieldwork. And in this case, this is from the master's thesis of my former student, Ann Center. And when she was doing her master's degree, she was interested in understanding whether there was a link between the occurrence of large wood in rivers, morphological units, in other words, like riffle, pool, run, glide, like the shape of the landforms in a river, and then how fish behave or what fish do with their life stages in those different areas as a function of wood and landform patterns. The y-axis on this plot is called red density. So reds are pods of fish embryos that are placed into a river by Pacific anadromous salmonid fish. So for example, Chinook salmon or steelhead salmon. And what this simple diagram shows are a variety of ideas about how Anne conceived that the phenomena would work. So the x-axis goes from some low density of wood. Notice we don't have any numbers. That's not important. We go to some high density of wood per unit reach. So the farther to the right you go, the more abundance of wood there is per unit area or length of the channel. On the y-axis is how many reds or how many pods of embryos are packed into the gravel over the same distance of length or area of a channel reach. The idea here is that, well, first of all, fish don't like pools at all, so there's not going to be much in pools. They might put some reds into runs and glides, but they're going to put the most into riffles. So first, there's a conceptualization that there's differentiation by landform. Okay, that's one idea. Then another idea is that they actually need wood. So in this idea, if you have no wood, then you're going to have very few to no reds, so they're low. As the amount of wood increases, we may still be deficient, but we're getting more and more utilization by the fish as there's more and more abundance of wood. Eventually, you'll reach the optimal level, so some range over which you have the perfect match to the size of the population of fish that's there. But then at some point, you could be packing so much wood in there that there's no space left for the fish to use. So the fish are like, I can't get to the gravel to put my eggs in there and create embryos, so now I'm stuck. So then the idea is if there's too much wood, then it would all be jammed up and the fish can't use that. So this is a very nice conceptual model. It has a simple experimental response to a driving function, and there's two different driving functions, wood density and morphological unit. So it doesn't matter whether the outcome proves this right or wrong. It just matters that you have a really good starting place to then understand the data you collect. Now, in terms of a transparent experimental design, it really helps if you lay out either a table such as shown here or a flow chart that presents how you're going to go about answering the questions you do. This is something that I rarely see, but it's something that I have my graduate students do, and it's something I challenge myself to do. When you take the extra effort and do this, you're ensuring that you know what you're trying to achieve, and you're increasing the possibility of having a positive outcome. So here on the left are the research goals. So there can be an overall goal, like goal 1 in this case, okay? Characterize the stage-dependent role of vegetation-induced roughness on river hydraulics, okay? And then in this case, there are 2 different questions associated with that goal. And then for each question, there's a particular test that's undertaken to then determine the outcome of the question. Now here, you don't see a hypothesis per se, but you could easily take the questions and transform them into hypotheses, have specific thresholds or outcomes here, and that would make it better. But this just gives you a feel for what this would look like, and you can look at all these goals on your own. Okay, so let's look at the type of field hydrology studies that exist. We're going to work through all of these. So here's just the first list. I don't need to say much about the list, but there's 6 broad suites that we're going to be looking at. I just realized that under 3, this number 4 should be an indent, and that should be B, because monitoring and measurement campaigns are a type of exploratory observation. So sorry about that mistake. Okay, first is a classical experiment. This is a great place to start because it's kind of the ideal. You know, you've probably all taken biology, chemistry, or physics laboratories. You've spent your 3 hours of an afternoon doing some classic experiment. You know, you write down your background, purpose, objectives, you methods, data, results, discussion, conclusions. Like you've done those lab write-ups in high school and college, so you have an idea of what this is like. Well, this is possible to do in hydrology. There are a wide variety of experiments that are being run that are impressive in their size, but they can be as small as a sponge. I have a little sponge experiment we do to test hill slope runoff in some of my other classes, or it could be as large as there's this facility in Arizona called the Biosphere 2 project, and they have massive scale experiments costing millions of dollars that are taking place inside there. Okay, so what is a classic experiment? It's when you try to have precisely controlled field conditions. That means that you have your well-defined control volume. Usually you've built that mass, that thing you're going to test. You then have the boundary. So the boundary is usually the air or air ground interface, or your water ground interface, or perhaps it's the soil bedrock contact. It just depends on what you're looking at. But you have those boundary conditions, so you have to know them. You also have to know the initial conditions. So if you have a watershed, what is the soil moisture throughout the whole watershed, for example, something like that. Then you're going to hold everything constant in the system, but just change one single factor and observe the effects. After you've done that for a variety of single factors, you might start looking at interesting combinations to see cumulative effects. But usually this is done initially just changing a single factor. When you do this, you need to carry out both control runs in which nothing has been changed and you just see how the system behaves normatively, and experimental runs in which you've applied the change. Another word for the change is a treatment. When you do this, you need to do replications. That is, you have to do it multiple times. Ideally you'd have many examples, so like not just build one experiment site or something, but build 10. And maybe you repeat the control like 10 times on 10 different examples. Another thing you could do is, of course, repeating the treatment. So just do it over and over again with slightly different ways of achieving the same thing. Maybe the areas that you affect are different, but in the same percent area or something like that. So you want to replicate and randomize as much as you can, both treatments and sites. And then ideally, you'd like to be doing a double-blind experiment in which the operators don't know whether they're collecting data from a treatment run or a control run. But of course, the reality is with the field kind of experiment, these are so big, you have to have your eyes open, and it's not like a placebo pill that looks the same as a real pill. Like you can usually see what's going on. So usually that isn't possible. It is possible, though, to have one team set things up and then the other team collecting the data. And it's also good, although you want to have a conceptual model in mind, it's possible that the people who you hire to work with you to collect the data, that they don't know it. On the other hand, if you do that, you face the risk that they simply may not be as dedicated to the work as you would be. And so, even though you might face a little bit of bias, my experience is it's easier to just let go any biases or preferences and just collect the data as is. Like, just be a drone and get the data, rather than putting the importance of your your important work into the hands of somebody you may not be able to trust to work on it as hard as you will. Okay, so let me show you an example of a classical experiment. And we'll do this by asking a question: does urbanization have a greater effect on the flash flood response of a watershed when you cover the ground with pavement? And you can do that in one of three places. You could do the uppermost area of the divide and hill slope noses, the planar hill slopes, or the low floodplains adjacent to the stream network. This is an important question because flash flood is a phenomenon that we have to worry about, and it is dramatically influenced by urbanization. It's just a topic I cover in HYD 143, for example. And urbanization is also going to be a theme of this course, like trying to understand what are the effects of human activities, societal decisions on the hydrologic cycle. The key test variable in this case, we're going to keep it simple. It's just going to be the time in seconds to start a flow at the basin outlet. Now, usually when we talk about the effect of urbanization, we're often interested in the peak discharge because that's often what does the most damage to the largest area that's subjected to flooding. However, having flow begin faster is another example of an effect of urbanization, and it's a meaningful one to look at. We're going to do three types of treatments. We're going to test 2 storm durations, either 1 or 2 minute storms. We're going to test 3 different intensities of rainfall, and this is going to be like a rainfall simulator sprinkling water down onto this experimental basin. And then finally, we're going to place impervious surfaces by covering over the ground with plastic, either on the divides, hill slopes, or floodplains. The approach is to build a scaled-down watershed in a test facility and place plastic patches over different regions during events. So here you can see an image of the design. It's from Schum et al. 1987. It's called the Rainfall Erosion Facility. It's in Arizona. It's a very large facility. I mean, like 15 meters. That's like about 50 feet long. What's that? I think that's a 7.1 meters wide. And then almost 2 meters deep. So we have this large watershed area, and then water gets funneled to the outlet so they can see the onset of runoff and the amount of runoff that's taking place. There's also walkways, and then there's a giant rolling carriage that can roll all the way across here. It's like wheels on either end, and then it can just roll over the top, which is a very impressive thing to be able to make measurements. In terms of the sediment, it's a mix of 50% real sediment and 50% sand. Okay, before we look at the results, think about it for yourself. Like, do you think that there'll be a greater effect on the divides, hill slopes, or floodplains? You might think, hey, well, on the divides, or the hill slopes. So the hill slopes are the steepest area. Maybe if you rain on the steepest area, it'll run off the fastest. Or the floodplains, they're pretty close to the stream outlet. Maybe proximity matters most. So I would suggest that you pause and just think about those questions before looking at the results. Okay, you've paused, and now we'll look at the results. So we've got a lot of different treatments here. We've got low intensity, medium intensity, and high intensity storms, 3 plots. And then in each one we have the 1 minute storm, 2 minute storm. Okay, the 1 minute storm is a dashed line, 2 minute storm solid line. And on the x-axis, 4 different scenarios. No treatment, so that's our control. Putting impervious surfaces on the divides, slopes, or floodplains. For the low intensity storm, you can see the start of runoff is anywhere from 80 to 140 seconds. And it's dramatically different. If we have an untreated case, we have the longest duration before runoff occurs. Even putting impervious cover over the divides significantly speeds up the start of flow. Putting it on the slope speeds up a little more, and putting it on the floodplain is the fastest. Now, there's no error bars here, so we can't assess from this plot alone the uncertainty that's here. But let's just take it for the moment that the floodplain is the one that has the fastest response. So it's the winner, so to speak. You can also see that for a longer storm, we get a faster runoff than for a shorter storm. Notice that a 1 minute or 2 minute storm is still less than the start of runoff. So the fact that a 2 minute storm is taking place, well, by 80 to 90 seconds, the first minute storm has already been off for 20 to 30 seconds, whereas a 2 minute storm has had an additional amount of time to rain, especially on the floodplain. So we can see there is a difference both with the cover and the intensity of the storm. Duration of the storm for low intensity events. Now, if we look at intermediate intensity and high intensity, there's no difference here at all. There does appear to be some difference between slopes for these intermediate events, but it's hard to say, again, what's statistically significant. Notice that the start of flow is faster for intermediate than low, and fastest for high intensity. So only 40 seconds before runoff begins. And again, whether there's any difference here is really hard to say. Maybe between these three and untreated, but it's really hard to say. Although there does appear to be some effect, potentially on slopes. So overall, why is this happening? Well, when you get to a high enough intensity, you're basically just saturating the watershed so quickly. Everything just saturates in a matter of well less than 30 to 50 seconds, and so as a result of that, then it didn't matter whether you covered it with plastic or not, because it was already going to saturate and have runoff long before it would make a difference, especially for the low intensity. So this is an important lesson. The effect of urbanization is greatest on smaller events, because smaller events are the places where storage makes a difference, like soil storage, depression storage, interception storage. Once you've exceeded the capacity of storage in a watershed, it doesn't matter what the cover is anymore, because it was going to run off as saturation excess anyway. So you can see the value of a classical experiment in being able to discern fundamental phenomenon about how watersheds behave in their delivery of water. The main advantages of a classic experiment: very rigorous. It should be replicable by anyone who can afford to do the same kind of experiments. And most importantly to me, it does get at the actual fine-scale mechanisms. You can get in there and monitor very carefully, especially with the technologies that we have available today, with like particle image velocimetry and laser scanning of these experimental facilities, or time-lapse photography, videos, all kinds of things that we can do that really allow us to understand these systems. Disadvantages, of course, we're not the same as chemistry, biology, and that. We're talking about very large systems, complex phenomena, life, water, dirt. It's hard. It's just very complex to reproduce or control. The bigger the system is, the harder it's going to be to control. Of course, outside, it's very hard to get permission to manipulate natural systems. We would have to provide environmental impact reports and show that what we're doing is okay. We also can't control major disturbances. We can, other than maybe fire, but we can't control hurricanes and earthquakes and things like that at field scale. Also, many things in hydrology, geomorphology, geoscience, they occur over very long time scales, and we can't run field experiments over those time frames. Okay, so if you need a break, this is a good time to pause and then come back, because now we're going to move on to the next one, which is model calibration and testing. This is a very different approach to science, because here the purpose of fieldwork is secondary. The main science and application is taking place in what we call model. This isn't the place to learn about models. Presumably you've already taken a number of hydrology classes and you know what the different kinds of models are. I've certainly covered it in Hydrology 143, so you can go look at the video podcast there if you want to see more about it. Here what we're trying to do is get the field data we need to prepare a model and then test it. The two main types of models we tend to use in hydrology are mass balance models to monitor fluxes and changes in storage in different areas of the hydrological system, or hydrodynamic models in which we're actually tracking both mass and momentum so that we can see depths, velocities, and other derivative variables like shear stress or habitat, things like that. Of course, there are many other kinds of models. There are landscape evolution models, for example. Of course, even if we're doing a groundwater model, it's a hydrodynamic model. We just have a very simplified form of momentum in that case, but it's implemented over a very complex three-dimensional sedimentary domain. So when you're calibrating first you have to prepare and calibrate, okay? So preparing, you're going to need the inputs. The inputs could be topography. They could be well logs that tell you about the structure of the subsurface. You might need input data like what is the influx of bed load. This is a bed load sampler. It could be having stage-discharge relations at a USGS gauging station. You also might need to know something about the three-dimensional structure or discharge measured with an acoustic Doppler velocity profiler. These are all technologies that we'll be talking more about later this quarter, and we've already covered topography and its characterization. Models also have something called parameters. Parameters are variables that relate to the structure of how water is distributed into, evapotranspiration or runoff or groundwater flow. And they're, depending on the complexity of model, well, it could be very simple, like discharge equals a parameter times rainfall intensity times watershed area. I mean, we call this the rational method, right? Q equals CIA. Well, C is a parameter, so you have to go out in the field, get data, and parameterize that. Here's an example of a very complex model with, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different parameters. Don't worry about what these letters mean. They're just different parameters in the model. There are different bars here. They represent 5 different watersheds that this test was done. So usually you're trying to get the best value for a parameter, and from different classes in hydrology or things we'll do this quarter, you'll learn how to do that. Once you do that, you often want to know, well, how sensitive is a model to the different values? So here we adjust the parameter by 10%, and we see what the model tells us is the change in runoff. We're going to call that error, but that's assuming we knew what the parameter value was in the first place. And you can see that this SQ variable has the biggest effect, although it is, the biggest effect is for Storage Creek. So 10% change in parameter leads to an almost 20% change in runoff. However, a lot of these are in the 5 to 10% change, which means that parameter error dampens the input error. Parameter error is damped to yield less percent error of runoff. Sorry. Okay, so what that means is you can start with a 10% error in a parameter, but if the output is less than 10% error, then it means it isn't a highly sensitive phenomenon. In fact, you're getting a substantial benefit there. So oftentimes we need data in order to figure out what we think the best values for these parameters should be. Let me show you an example of model calibration and testing. Usually what you want to do is have some kind of validation data. So you're going to make a model. It's going to predict something like how much flow there's going to be or where landslides are going to occur. And then in the field, you want to have data that tells you whether that was correct. So in the left, here's time series at a watershed outlet, and the x-axis is time. The y-axis is either on the left, the runoff, or on the right, the rainfall. And so the bars that are coming down are the intensities of rainfall, which are here like, generally like 0 to 2. And then this is precip, so it's like millimeters divided by tenths of a millimeter. And then the runoff here is given in millimeters per day. And you can see that the solid line is the simulation and the dotted line is the observed. And so, we've collected this observation data to see how well the model's doing. And you can, visually decide for yourself whether you think it's good or bad. That's not important right now, but it's just that this is what you can do. Over on the right is a map of a watershed. It's a contour map. And what you can see here is the stream network shown in blue. This is the perennially flowing water. And at the heads of the channels are locations shown in green that are thick colluvium and hollows. And then the red are actual landslide scars. So this is a map that shows where landslides have occurred relative to the locations of sediment fill at the heads of channels. And if one were to then run a landslide prediction model, and there's, for example, one called ShallStab, but there's many others, then you could use this field observed data to test whether that model was performing well or not. Calibration and testing has a variety of pros and cons. And as you can see, while the list of cons is pretty long, but they're very important pros. And first of all, they allow us to get a large-scale, long-term phenomenon. There's just no other way to do this, and so we're going to need to have numerical models. And in fact, they've become a real mainstay of understanding hydrology. Also, models give us the ability to turn on and off different hydrological forces. That's a very powerful tool to be able to play that game and see how nature would work in different combinations. And finally, many models in hydrology are what are called physics-based models. That is, that they apply the laws of mass, momentum, and energy conservation. And we think that those are very important, that they hold true in the universe as we know it. Now, there are many disadvantages, and the disadvantages largely relate to the fact that models aren't reality. They are simplifications that are missing often essential elements that we may not realize or understand how to account for. But still, they do very well. They really give us ability to predict what's going to happen. I mean, I may not know whether there's going to be a hurricane tomorrow or not, but it's really great if the weather service is telling us, there's a 50% chance that this might happen. Then at least I can prepare. And if it's wrong, well, no harm, no foul, I guess. I did spend a little bit of money, but it really makes a big difference to society to have numerical models. Unfortunately, there are a lot of problems with them. The parameters to models are oftentimes not realistic at the scale at which a model is being operated. So we have to think about that, and then how do you measure, estimate, calibrate something that may not even be real. If we're going to use data to test a model, we better be darn sure that that is good data. I can tell you many times data is pretty darn crappy, and it's just inherent human nature to believe data, no matter how crappy it is, because people don't know that. They just hear data and they take it to be the truth. Whereas you take a model, people are inherently skeptical of models, and so they're going to assume it's wrong. So if you see a difference between what's observed and what's predicted by a model, is that the model's fault or is that the data's fault? It's important to have estimates of uncertainty or error in both data and models. The simulations, they only have the physics that we put in there, so they're not going to be able to see inherently new phenomenon that we haven't programmed into it. Also, sometimes models become so large, they have so many parameters that you can get any outcome you want simply by mixing and matching different parameter sets. And at that point, the model is just sort of almost useless because you don't really know what's real anymore. Sometimes there may not be that's basically just there may not be a unique solution to the problem because of all the parameters that are there. Or you could just have so many parameters that it's very hard to calibrate in a meaningful way. Like calibrate means to tweak one parameter to match observed data. Well, how are you going to calibrate something if you have 30 parameters? Again, you can tweak that to get any outcome you want. And then finally, some models are now so large and complex that whether they're truly replicating nature or not, the fact is they're just too complex to understand. So we might as well just get out in the field and see what's actually happening in real nature rather than just seeing what a model is. One of the biggest problems with models is they lead us to engineer the world to fit the models rather than engineering for the real uncertainty and variety of what exists in nature. Okay, the next type of field work is exploratory observation. This is a very broad class, and it has to do with the situation in which you have a highly complex system and relatively little knowledge about it. So you just want to, of course, have some conceptual model to start with, even if it's highly uncertain, but get out there and start measuring the basic system variables that drive the phenomena that exists, and then start to establish correlations and statistical relationships that firm up how the system is functioning. For this to be productive, you still have to have clear goals and a carefully considered experimental design. And I'm going to show you 4 different approaches to exploratory observation. The first is what I call a stratified landscape experiment. In this approach, you're going to use a formal statistical design to divide the whole area that you're studying into different homogeneous units. And then you're going to compare those units. And those comparisons might be tests for the mean condition or variance, or it could be a variety of statistical approaches. It could be a cluster analysis. It could be a multivariate method like principal components analysis to get at the underlying variables. There's a lot of different ways to go about it. What you're going to do once you've stratified the landscape and understood the basic variables that are there is then monitor the processes that are taking place and try to see how those processes vary between the different strata. What this approach does is it reveals the overall system functioning of each unit, and then you can infer the fine-scale mechanisms based on how different units behave. A simple example of this would be if one wanted to characterize the groundwater resources or groundwater contamination of the whole state of Maryland. So here's a map of Maryland that shows different geological provinces, geological physiographic provinces. You can see them shown here. There's 4 main provinces that are shown. Now you can imagine that if we just did a random sampling across this whole thing and ignored the geological provinces, then we might get a very biased result because random sampling will not yield an effective characterization of all of these different domains. For example, it might be more meaningful to have 10 groundwater sampling locations in each unit type, regardless of the size, than it is to have 40 overall. So if I have 40 samples here, getting 10 tidal marsh samples would really well characterize the conditions in the tidal marsh. 10 might be enough to get the coastal plain sediments or other provinces too. And I'm just throwing out 10 as just no particular reason, but just to illustrate the point. So trying to decide what is the primary basis for stratifying whatever it is you're monitoring is really, really important. It could be a result of a landform or geology. It could be a result of vegetation. It could be a result of precipitation patterns. That's something that you have to decide. One specific type of stratified landscape experiment is when you're going to just have 2. And so this is what we call a paired basin study. In a paired basin study of 2 watersheds, that, or more, could be more, but you have two that essentially are the same. They're next to each other, or they're the same in all the ways that you can discern. And now you want to experiment on one of them. So instead of doing it in the laboratory as a classical experiment, this is as close as we can get to in the field. So we have two watersheds, in this case, in this illustration, side by side. We're going to have a calibration period. That means that we're just going to let nature take its course for a period of time, 5, 10, 20 years, just depending on how dedicated we are, how long we think we're going to live. Monitor the system and establish how they work relative to each other. So this plot shows here the discharge coming out of this control watershed, QC here. Okay, that's on the x-axis. And the discharge on what's going to become the experimental watershed is on the y-axis. So the flow out of the experimental watershed is very predictable from the flow out of the control. Notice it's not a one-to-one relationship, so we actually maybe have a little less. You can see lower values here than there, but it's highly predictable. That means that we can predict what we expect to happen in the experimental watershed in the natural state based on what's happening in the control watershed, okay? This is a very important concept, because once we're going to change the experimental watershed, we don't know what its natural condition is, so we're going to rely on this function to predict it. So now in the test phase or treatment period, we're going to say cut this watershed. Okay, change it in some meaningful way. Remember, change one variable. In this case, typical experiment is to deforest it and then apply herbicides to keep trees from coming back. Maybe there's some extra grass here. And then this is going to have whatever effect it's going to have. And so we're going to have now new data. The new data is what happened in the experimental watershed, what happened in the control watershed at the same time. We're going to take the data from the control watershed, apply it to this function that we already established, and get our prediction of what would have happened in the experimental watershed had we left it alone. That's QX hat. This is the essential concept. If you don't understand this now, then watch this, pause, go back, think about it. The key is we need to know two things about the treatment watershed. We need to see, of course, what happened when we treated it, but we have to have an idea of what would have happened if we left it alone. And this function tells us that. And then as a result, the difference between what actually happened and what would have happened if we left it alone is the effect of the treatment. And that's shown here. Okay, so here's an example of a paired basin study. It's a very classic study done in Hubbard Brook, which is an experimental watershed associated with Harvard. You can see here data from 1965 to 1968. The x-axis is month, so June, July, August, September, and so on. So for a period of about a year, December, no, that's January. Okay, for half a year, they just monitored it. It isn't a very long time, but anyway, you can see that the two watersheds are pretty much mimicking each other. And then all of a sudden here, at the beginning of the year, they clear cut one of the basins. And that's watershed 2, that's going to be shown with the dashed line. Watershed 6 was left alone. At first you don't see much effect. There's some just different wiggles, but really changes in the summertime. So you see a systematic shift where watershed 2 has substantially higher runoff in the summertime than watershed 6. In the wintertime, they sync up again, and then in the summertime, they differentiate each year. So you can see that there is an effect, but the effect is isolated to just the summertime. Why? Why would there be a difference in the summer or the winter? I would suggest that you pause here and reflect on that. Try to think of why you think that is. Okay, I hope you've thought about it. The answer is that it's similar to the classic experiment. Remember in the classic experiment, we didn't see an effect of a change in intent of covering the ground of an unvegetated watershed, making it impervious if there was a very high intensity of precipitation. So one possibility is that during the winter, you have such a high intensity of precipitation that it doesn't matter again what the cover is, so cut or not cut. However, that isn't entirely panning out, because when we look at the range of intensities here, they're not different during this, this first year after the clear cut. In the second year, there is a very large intensity storm, but it in fact does show differentiation. So this cannot be the explanation. What can be the explanation is something else that happens in New England during the winter and the summer. And that is that two things. One, leaves versus no leaves. So if we have a deciduous forest, then during the wintertime it will lose all of its leaves, and therefore whether you're forested or deforested has less of an effect because the branches and trunk have relatively low storage. However, when you have lots of leaves out there, you get a lot of interception, you have high evapotranspiration rates, and so you can have a significant absorption and release of water to avoid runoff. And that's what you're seeing here, is that during the summer, the forested watershed 6 is able to get rid of that water without having to have runoff, whereas the deforested watershed 2 is not. So there's a very big difference in that. There also could be effects in terms of snow and whether being forested or deforested with deciduous trees would make any difference or not, but that's another factor. When we look at the chemistry of what's in the water, there's also significantly higher concentrations of stuff coming out of the watershed in the logged watershed than before. And so these different dots here illustrate whether there's a significant change or not. Okay. Another variety is like a paired basin, but instead of having two basins, if you have a very large watershed, you're just not going to find a fair pairing to go with it. So in that case, you might do something like a before-after control study, before-after control impact, or BACI as some people call it. So in this case, you might have a lot of data, and then something happens to a watershed. It gets urbanized, a dam is built, it's disturbed, something happens, and if you have long enough data before and after, then you can see what the change was. Now this only works if the functioning of the system is the same before and after. So in other words, the driving climate and tectonics, like the geology, topography, like everything else has to remain the same except one thing or some set of things, but you can't fundamentally change like all the drivers. So for example, if the land is being subjected to climate change such that there's interdecadal changes in conditions, then you have a problem because now you have what we call non-stationarity, and you'd have to at least remove those trends first before you look at these effects. So there can be ways of dealing with it, but you have to be careful about that. So here's a very simple example. This is a commonly used method for studying the effects of dams. And here's a time series from 1904 to 1964, and then 1964 to 2000, showing the stream flow discharge for the Mokelumne River this whole watershed. So it's a couple thousand square kilometer watershed. You can see a lot of periodicity in here and values up to almost 25,000 CFS. And then you can see that when Pardee Dam was built, there's a fundamental change. There are now bunches of years where there's no big flows, and then only a few years with some big flows. And then a second dam was built, and now it's completely chopped. So there's never a flow bigger than 5,000 CFS in this data. And you can see there are long periods where there's near zero flows that are taking place. So there are a wide suite of statistics that can be used. There's whole software packages here. It's part of a study approach called the natural flow regime. And there's a famous paper by Poff, 1997, that you can look at, as well as software that's available for doing this kind of work. And we covered a lot of this in HYD 143. It's not important to know here. So when you have a stratified landscape experiment or study, the main advantage of this approach is you have some control. Like, you're not entirely hopeless in what you're doing. You're mindfully stratifying it into different units. You're monitoring things in a very process-based way to get at the key phenomenon that you're interested in. And you could do this over a fairly large scale. The biggest problem with the approach is people tend to be overconfident. Just because you say that the number one difference between two watersheds is one's vegetated and one isn't, it doesn't mean you're right. There could be dramatic differences in geology, soil conditions, and maybe one has like an army of gophers digging holes in the ground that you're not aware of, or maybe one's in a rain shadow, or different aspects, slope conditions. There's a variety of things, and so it's important to use rigorous statistics to prove that your pairing or stratification is reliable and appropriate. Okay, so the next type of exploratory observation is called monitoring and measurement campaign. Here we're still going to use a formal statistical design to establish an array of monitoring stations, but now we're not going to have a basis for comparison. We're just going to watch to see how the system functions through time. You might still be able to look before and after changes when events come through, or if there's changes in land use, but you're just at a spatial scale where there isn't anything to pair against. Or you might be looking in such detail that at that level of detail, even in a small area, two areas are quite different. Often what we want to do here is quantify the processes that are taking place in terms of the magnitude and frequency of the events that are taking place. We could also be interested in the duration, the rate of change, or the timing and predictability of those things. So those are all the elements of what we call the natural flow regime, as I mentioned before. There are many types of analyses that are possible. It just depends on having a strong conceptual design, and then most importantly, adhering to that through the study. The most common problem with monitoring and measurement campaigns is that people lose interest or they change their ideas, and so you then get a moving target. Sometimes it's best to keep collecting data to prove that something is wrong, and then make a systematic shift at an appropriate time when you can do that. Here's a classic example, sticking with the theme of urbanization, that shows the effects of urbanization on a stream's hydrograph. Before, the classic experiment showed that the start of runoff came sooner when we urbanized, and it didn't matter where we did. If it was a low-intensity storm, we saw that effect. So there was data that was collected 1939 to 1960 and published by Espy in 1969 that looked at Bray's Bayou, which is one of the most densely urbanized areas in Texas. It's around Houston. It's a stream network. If you go and look for it on Google Earth, it's just shocking when you look at what it looks like today. It's a fully urbanized area. In this case, this is a plot that shows what we call a unit hydrograph, which is the stream flow resulting from 1 inch of rain excess applied over a basin uniformly and at a uniform rate for a set period of time. So for this unit hydrograph, if we start with a 1939, which is the line with the 3 dots, and then this is discharge in hundreds of CFS, you can see that it takes a period of time, like about 7 hours after the start of rainfall excess before runoff begins. We reach a peak under 2000 CFS or 2000 CFS. And then it has a long base that goes well beyond 85 hours. If we go to the other extreme, 1960, the response comes very quickly in 1 to 2 hours. It reaches a peak that's 2.5 times, almost 3 times, 3 times the original level. And then it drops abruptly, and it can reach its end even before we reach 85 hours. So the delta T here is the same effect that we saw in the classic experiment. But by monitoring for more than just the start and looking at a real world example, we saw 3 other important effects. A faster time to get to the peak after the start of rainfall excess, a higher peak discharge, and more total volume of runoff. So this shows the power of a monitoring campaign when done very thoroughly over a period of time to see change take place. Another example, here's a wetland that I studied during my PhD. There are a variety of different strata here indicated by the different colors. The pluses are different sampling locations, and there's not a lot of different sites in some of these, so I wouldn't say it's a well stratified. It's well stratified, but not well sampled in each strata, just because of the cost associated with that. What you can see here is sampling every other week over an almost 2-year period, and on the y-axis is the amount of sediment that accumulates on the ground in this wetland, grams per square centimeter. It's per 2 weeks, but I'm normalizing it to a year basis to get it to be sizable numbers. If you just look at the raw data, you don't see any patterns. But if I stratify it by a landform type, and then I run tests to see what's meaningful, in fact, we find statistically significant differences in the mean sedimentation rate between the different landforms that are out there. So the advantages of a monitoring and measurement campaign is that this is basically the only way to go when you're looking at large systems or you're looking in very great detail. It allows for the analysis of the most complex phenomenon. That's just kind of what we need to do. And most importantly, we're taking the real world as it exists. We're not trying to change it or think of it a different way. We have to just come to grips with reality. And my experience is that's very important. Unfortunately, of course, we have the least control of the system, and the results you get can be strongly dependent on who's designing the project. How well have they thought through what they're trying to do, and how successful have they been with that? And most unfortunately, this isn't something that you can replicate. So people in different parts of the world will publish the same kind of study over and over again, but they might get different outcomes because of the different settings. Okay, we have 2 more methods to go. The first is paleo-environmental reconstruction. You may not think of this as hydrology, but it is, because usually we might be looking at, say, a groundwater context, and we need to understand something about how water is stored or moves through the ground as part of hydrology. Reconstructing the history of how the ground was formed is very important to understand the processes that are taking place. So we might be going out and collecting cores, which could be installing wells or creating logs. And when we collect sediment out of the ground, we can see sediment, the grain size distribution, orientation. We can assess erosion deposition mechanisms, patterns that we see, such as bed forms. Fossils might be in there. We might see seeds or pollen grains, plant animal fragments. This could be ice, or it could be dirt. You might have pore water that's present that you can sample for its chemistry, its isotopes. There's a lot of things that you can do. So for example, here's a section of core, opened it up, and what you can see here, like charcoal fragments, tells us something about the frequency and intensity of fires. We have fine sediment deposits, so that's like mud here. Could be from a change in land use, a sand lens that might be representative of a flood event, and a full fragment of wood that we could use to get an age date for when that wood died. One thing that comes out of a paleo-environmental reconstruction is a conceptual model over a long term that you can then use as an input from your historical analysis. And here's a very famous conceptual model that comes from understanding the effects of European colonization in North America. So you might have had streams that were present over the land with the floodplain. During the agricultural period, there was so much logging throughout a watershed that a lot of sediment came down and filled in the floodplain. That filling in may have separated the channel from the floodplain. And then in a modern period, now we may be going on top of here and urbanizing that, as we may also be urbanizing enough for the watershed to decrease the sediment supply, and the decreased sediment supply plus the increased runoff from urbanization would lead to incision of the channel, destabilization of the banks, and then harming the urban areas. So this is a very common problem. Like, you've got some shopping mall or parking lot or road, and it's being impacted by a destabilized riverbank. Well, why is that happening? Well, maybe because of 100 years of how people have used the land, not related to just one simple thing that took place last year. So the main advantages of paleoenvironmental reconstruction is that it enables you to get at the long-term dynamics that are not accessible in any other way. You just can't monitor the history. You have to go out and reconstruct it. Having a historical framework, as I showed in the historical analysis presentation, it really gives you a good starting point for understanding the system and thinking through what measurements you should make that are meaningful today. Definitely helps you understand the style of geomorphic and hydrologic functioning of the system. Unfortunately, it's not an easy thing to do. Unless you're a specialist in that or you're collaborating with specialists, then it's hard to accomplish this. But it's really important to be aware of it and know that you need to find those kinds of specialists. Just like in crime scene investigations, there are specialists who can do all these same kinds of reconstructions. Well, we need that for environmental studies as well. And then the very last method, and we're not going to go into much about this at all in this class, but remote sensing. And I already covered it some with the geographical positioning methods. On the left is a LiDAR image, a 2.5 meter resolution. I mean, just this glorious watershed map. On the right is a map that's classifying the land to get at the storm damage assessment. Remote sensing is incredibly powerful. It's becoming more and more powerful. It's becoming less and less expensive. It's one of the most important developments in the beginning of the 21st century that is very central to the future of hydrology. And so it's going to be a field method. It's not necessarily tied to, in the way I'm presenting with a particular approach to field work or theory, but you're going out and getting that data. That could be an input for model calibration and testing. It could help you to set the stratification for a stratified landscape study or something like that. So overall in this chapter, I've given you 6 different major approaches. Really what we had classical experiment, we had model calibration and testing, and then we had exploratory observations. It's really 3 main things, but under exploratory observation, we had several other ones. We had a stratified landscape experiment, measuring monitoring campaign, paleo-environmental, and then reconstruction, and then remote sensing. So anyway, however you want to add it up, there's no one approach that's going to solve all the problems, but it's essential to have one. Like, know what you're doing before you go out in the field. And we're going to be switching now to actual methods, and so you'll be ready, of course, to jump in the field. But it's just essential that you have a conceptualization for what you want to do. And every time I present a study for the rest of this course, ask yourself, what kind of approach are we looking at? Is it a model calibration testing? Is it a classical experiment? And I promise you, this is going to come up in homeworks and examinations and stuff to understand, because I really want you to tie back to these concepts and remember them.